What if I told you that the rock-solid reality you experience every single day, the chair you're sitting on, the air you're breathing, the linear flow of time from yesterday to tomorrow is just a grand illusion? A user interface designed for creatures of our scale, hiding a truth so bizarre, so profoundly counterintuitive that it sounds more like science fiction than science fact. This isn't a conspiracy theory. It's the central, unsettling message of our most successful scientific theory ever, quantum mechanics. This is the theory that powers your smartphone, your GPS, and the medical imaging that saves lives. It is accurate to an astonishing degree. And yet, at its very core, it presents a picture of a universe that seems fundamentally broken. It's a glitch in the code of reality. These aren't just minor bugs. They are deep philosophical paradoxes that tormented the very geniuses who discovered them. Albert Einstein called one of its effects spooky action at a distance. Erwin Schrödinger, of the famous Cat in a Box, admitted, "I don't like it, and I'm sorry I ever had anything to do with it." These are the cracks in the foundation of existence. And today, we're not just going to peek through them. We're going to dive headfirst into the abyss. We will explore the deepest and most disturbing paradoxes of the quantum world, the signposts that tell us our entire map of the universe might be wrong. Let's start with our understanding of time. It's simple, right? The past is fixed. A cause happens, then an effect follows. You drop a glass, then it shatters. You can't unshatter the glass by changing your mind about dropping it. But what if you could? What if a choice you make right now could reach back in time and rewrite a historical event? Welcome to the delayed choice quantum eraser, an experiment so mind-bending it feels like a violation of cosmic law. It builds on the famous double-slit experiment, where a single particle, like an electron, is fired at a screen with two slits in it. If we don't watch which slit it goes through, the particle behaves like a wave, going through both slits at once and creating an interference pattern on the detector screen behind it, a series of alternating light and dark bands. But if we place a detector at the slits to see which path it takes, the particle instantly chooses one path and acts like a solid little ball, creating just two simple bands on the screen, no interference. The weird part is that the particle seems to know if we're watching. But the delayed choice quantum eraser takes this weirdness and dials it up to an existential crisis. In this version, we let the particle pass through the slits and hit the final screen, recording its position. The event is over. It's in the history books. Only then, long after the particle has finished its journey, do we make a choice. We can choose to look at the which path information that was gathered at the slits, or we can choose to erase that information. Here's the impossible part. If we choose to look at the information now, the pattern on the screen, which was created in the past, will show two solid bands the particle acted like a particle. But if we choose to erase the information now, that very same historical pattern will magically resolve into an interference pattern. The particle retroactively acted like a wave. Let that sink in. A decision made in the present dictates the fundamental nature of an event that has already concluded. It's as if you walked on a beach, and then, by deciding whether or not to look at your shoes back at your hotel, you could change the footprints you left in the sand from a single set of prints into a washed-out wave-like smudge. It shatters our notion of linear causality. The past is not a fixed, immutable record. It appears to be a shimmering, unfixed canvas that can be repainted, at least on the quantum level, by the choices of the present. The arrow of time, it seems, may not be as straight as we once believed. If the past isn't fixed, what about reality itself? We assume there is one single objective reality that we all share. If a tree falls in the forest, it either fell or it didn't. Two people might disagree on why it fell, but not on the basic fact of it being on the ground. But quantum mechanics challenges even this bedrock assumption. Enter the thought experiment known as Wigner's friend. It's a story of two observers and two realities. Imagine a scientist, let's call her Anna, inside a perfectly isolated laboratory. Inside her lab, she performs a quantum measurement on a particle, like checking its spin. The particle, before she measures it, is in a superposition. It's both spin up and spin down at the same time. The moment Anna measures it, the superposition collapses and she sees a definite result. She jots down in her notebook. At 3 p.m., the particle was spin up. For Anna, inside her sealed reality, a fact has been established. The uncertainty is gone. But now, let's consider her colleague, Wigner, who is standing outside the sealed laboratory. From his perspective, he has no idea what happened inside. Because the lab is perfectly isolated, quantum mechanics says that he must describe the entire lab, including Anna in her notebook and the particle, as one giant quantum superposition. In Wigner's reality, Anna hasn't seen a definite result. Instead, she is in a bizarre quantum state of both Anna-who-saw-spin-up and Anna-who-saw-spin-down, existing simultaneously. So we have two records of the same event. Anna's notebook says a definite thing happened. Wigner's calculations say nothing definite has happened yet. It's all still a cloud of possibilities. Who is right? The paradox is that according to the rules, they both are. Anna's reality is real for her. Wigner's reality is real for him. It's only when Wigner opens the lab door and asks Anna what she saw that the giant superposition collapses for him, and their realities finally sync up. This thought experiment forces us into a deeply uncomfortable corner. Does an objective reality even exist, independent of an observer? Or is reality a personal, subjective experience? Can two different, contradictory truths exist at the same time, both being correct from their own frame of reference? It suggests that the universe doesn't have a single definitive story. It has multiple drafts, all coexisting until a conscious observer reads one of them into a fixed state. The delayed choice experiment hinted that time is a two-way street. Retrocausality takes that idea and runs with it. It proposes that not only can the present influence the past, but the future can influence the present. At a fundamental level, the mathematical equations of quantum physics are time-symmetric. They work just as elegantly whether you run the clock forwards or backwards. It's like watching a video of a perfectly elastic collision between two billiard balls. You can't tell if the tape is playing in forward or reverse. Our universe seems to have a deep-seated preference for this kind of symmetry. The arrow of time that we experience, the relentless march from past to future. The reason why eggs don't unscramble seems to be an emergent property, not a fundamental law. Retrocausality explores the implications of this time symmetry. It suggests that when a quantum particle is faced with a choice, say, which path to take, its decision might be influenced not just by its starting conditions, but by the measurement that will be performed on it in the future. It's not that the particle knows the future. It's more that the entire timeline of the particle, from its creation to its final measurement, is a single, self-consistent story. The beginning helps to write the end, and the end helps to write the beginning. This doesn't mean you can send lottery numbers back in time to your past self. The influence is subtle and statistical, woven into the probabilistic fabric of quantum events, and it doesn't allow for the transmission of information. But it completely changes our understanding of cause and effect. We think of an event as a domino falling, triggering the next one in a neat line. Retrocausality suggests it's more like a completed crossword puzzle. The answer you write for one across is constrained by the letters you'll eventually fill in for 2 down and 3 down. The entire story of an event is co-authored by both its history and its destiny, and the clear line we draw between past and future might be the most human illusion of all. If the boundaries of time are blurry, what about the boundaries of space? We assume that for two things to influence each other, a signal must travel between them, limited by the speed of light. If two people are in separate, soundproof rooms, they can't coordinate their answers to a question. That would be impossible, unless they shared a secret connection that defies space itself. This is the reality of quantum entanglement, a phenomenon Einstein famously called spooky action at a distance. When two particles are entangled, they become a single unified system, no matter how far apart they are. Measuring a property of one particle, like its spin, instantly, and I mean instantly, influences the corresponding property of the other, whether it's across a lab bench or across the galaxy. This isn't just a theory. It's been demonstrated in experiments known as quantum games. Imagine two players, Alice and Bob, in completely isolated rooms. They can't communicate in any way. In each round of the game, they are each asked a random question and must provide an answer. The rules are designed in such a way that if they were using any classical strategy flipping a coin, following a pre-agreed set of instructions, they could only win at best 75% of the time. It's a mathematical certainty. But if Alice and Bob each hold one particle from an entangled pair, they can win 100% of the time. They perform a measurement on their particle based on the question they receive, and the outcome guides their answer. Because their particles are entangled, their answers are perfectly correlated in a way that beats the classical limit. They are coordinating their actions without exchanging a single bit of information. It looks like telepathy, but it's not. No signal is sent. So what is it? It's a profound non-local connection. It reveals that the universe is not a collection of separate, isolated objects. At a fundamental level, it is a deeply interconnected web. The idea that two things are separate is an illusion created by distance. Entanglement shows us that in the quantum realm, there is no here and there. There is only a single, unified, and mysterious whole. It forces us to reconsider what it means for anything to be truly alone. We think of an object as a unified thing. A cat is a cat. Its properties, like its weight, its color, and its purr, are all part of the cat. They go where the cat goes. You can't have a cat walk down one street while its purr travels down another. That would be absurd. And yet, in the quantum world, this very absurdity has been proven to be true. This paradox is named after the Cheshire Cat from Alice in Wonderland, who could vanish leaving only his grin behind. In a stunning experiment, scientists managed to do something similar with a neutron. A neutron is a subatomic particle, and it has an intrinsic property called magnetic spin, sort of like a tiny built-in bar magnet. In this experiment, they set up a device that could gently measure the path of the neutron and, separately, the location of its magnetic spin. They sent a beam of neutrons through an interferometer, a device that splits a particle's path and brings it back together. The results were dumbfounding. Their instruments showed that the neutrons themselves traveled down one path, while their magnetic spin traveled down a completely different path. The particle was in one place, and one of its own fundamental properties was in another. The cat went one way, its grin went another. This paradox demolishes our classical idea of what an object is. It suggests that a particle isn't a solid little dot with properties stuck to it, like decorations on a Christmas tree. Instead, a particle seems to be a collection of abstract properties that are bundled together in what we call reality. But under the right quantum conditions, that bundle can be teased apart. It begs the question, what are we? If a fundamental particle can be separated from its own essence, what does that say about the objects of our everyday world? Are we just temporary collections of properties, loosely held together by the laws of physics? The quantum Cheshire Cat suggests that the very definition of a physical object is far more ghostly and fragmented than we could ever imagine. This next one is perhaps the most personal and existentially terrifying paradox of them all. It's a thought experiment that takes the many worlds interpretation of quantum mechanics to its ultimate, unnerving conclusion. The many worlds interpretation, MWI, is one proposed solution to the measurement problem. It says that when a quantum measurement is made, the universe doesn't collapse into one reality. Instead, the universe splits. Every possible outcome happens, each in its own separate parallel universe. If a particle can be spin up or spin down, Then in one universe, you measure it as spin up, and in another, a perfect copy of you measures it as spin down. Now, let's build the quantum suicide machine. Imagine a gun pointed at your head. This gun is wired to a quantum measurement device. Each second, the device measures a particle's spin. If the particle is measured as spin up, the gun does nothing. It just clicks. If it's measured as spin down, the gun fires. There's a 50-50th chance each second. You sit in the chair and start the experiment. In the first second, the particle is measured. According to MWI, the universe splits. In one universe, the particle is spin down, the gun fires, and your story in that branch ends. In the other universe, it's spin up, the gun clicks, and you survive. You're still there, heart pounding. Another second passes. The universe splits again. In one branch, you're gone. In the other, you hear another click. You continue this. After 10 seconds, the odds of surviving are less than 1 in 1,000. After a minute, they are astronomically small. From an outside observer's perspective, they would almost certainly see you die within the first few seconds. But here's the twist. You can only ever experience the timeline where you survive. Your stream of consciousness, your first-person perspective, will, by definition, only continue in the branches of reality where the gun doesn't fire. From your point of view, you will sit in that chair and hear click, click, click. Again and again, defying impossible odds. You will never experience your own death. You will become, from your subjective viewpoint, immortal. This is quantum immortality. It suggests that your awareness will always follow the path of survival, no matter how improbable. You might find yourself the sole survivor of a plane crash, the one person who miraculously avoids a global pandemic. You would witness yourself living on through increasingly strange and desolate timelines, watching the world and everyone you know age and decay around you, forever trapped in the one improbable branch where you just happen to make it. It's a lonely, horrifying kind of immortality, born from the cold logic of quantum branching. For decades, we have relied on two monumental theories to describe the universe. Einstein's general relativity, the theory of the very large planets, galaxies, and the curvature of space-time. And quantum mechanics, the theory of the very small particles, probabilities, and weirdness. For the most part, they stay in their own lanes. But there is one place in the universe where these two titans are forced into a cage match at the edge of a black hole. And the result is a paradox that threatens to break physics itself. Here's the conflict. A core principle of quantum mechanics is that information can never be truly destroyed. It can be scrambled, like burning a book. You can't read the words anymore, but in principle, if you could collect every particle of ash and smoke, you could reconstruct the original book. The information is still there. Quantum mechanics insists this rule is absolute. But then Stephen Hawking entered the scene. Building on general relativity, he discovered that black holes are not truly black. They slowly leak radiation, now called Hawking radiation, and over immense timescales, they will eventually evaporate completely, leaving nothing behind. So, what happens to the information of all the things that fell into it? If you throw a book into a black hole, general relativity suggests its information is trapped inside, beyond the event horizon, lost to the outside universe forever. But when the black hole evaporates, where does that information go? It can't be in the Hawking radiation, because that radiation was thought to be random and thermal, carrying no information. It can't be left behind, because nothing is left behind. It seems to have simply vanished. This is the black hole information paradox. We have two of our most fundamental laws giving us completely opposite answers. One says information is immortal. The other creates a scenario where it is utterly annihilated. It's the biggest contradiction in modern physics. It tells us that, for all our progress, we are missing something huge. There is a deep gap in our knowledge, right at the violent intersection of gravity and the quantum world, And solving this paradox may be the key to the next great revolution in science, a true theory of everything. We've journeyed through paradoxes of time, reality, space, and identity. But all of them, in one way or another, lead back to one central unresolved mystery, the measurement problem. It is the beating, haunted heart of quantum mechanics. As we've discussed, before we look, a quantum system exists in a superposition, a ghostly haze of all its possible states at once. The electron is neither here nor there. It is everywhere it could be. The cat is both alive and dead. The world is a blurry landscape of pure potential. But the moment we perform a measurement, the moment we look, this entire cloud of possibilities instantaneously collapses into a single concrete reality. The electron appears at one specific point. The cat is either alive or dead. The ghost becomes a machine. The problem is this: the theory of quantum mechanics provides no explanation for this collapse. The core equation, the Schrödinger equation, describes the smooth, wave-like evolution of possibilities. It never shows them collapsing. The collapse is a separate, ad hoc rule that we have to tack on to make the theory match our observations. It's a fudge factor that just says, and then magic happens. What constitutes a measurement? Does it have to be a conscious observer? A human? A cat? Or will a simple, unconscious Geiger counter do the trick? When, precisely, does the collapse happen? And why does the universe bother to play by two different sets of rules? The smooth, probabilistic dance when no one is looking, and the abrupt, definite jump when someone is. This is the measurement problem. It's the unresolved question of what turns the ethereal world of quantum potential into the solid reality we experience. It's the dividing line between the strange quantum realm and our familiar classical world. And until we can explain it, we can't truly say that we understand reality at all. So, where does this leave us? We've seen that the past can be rewritten, that reality might be subjective, that the future can influence the present, that space is no barrier to connection, and that the line between possibility and actuality is a mystery. Each of these paradoxes is more than a mind-bending puzzle. It's a flare sent up from the front lines of physics, signaling the absolute limit of our current understanding. Our most cherished assumptions that time flows in one direction, that objects have definite properties, that a single objective reality exists, these are the very things quantum mechanics asks us to question. The universe is not the predictable clockwork machine that classical physics described. It's something far more mysterious, interconnected, and strange. But this shouldn't be a cause for despair. It should be a cause for wonder. These paradoxes are not failures of science. They are invitations. They are the universe's way of telling us that our journey of discovery is far from over. They are the breadcrumbs leading us toward a deeper, more profound truth. So, what can we take from this into our own lives? First, embrace uncertainty. The universe is, at its most fundamental level, a realm of probability and potential, not rigid certainty. In our own lives, we often crave definite answers and fear the unknown. But perhaps we can learn from the quantum world that uncertainty isn't a flaw. It's the space where all possibilities are born. Second, question your assumptions. Our common sense is an incredibly useful tool, but it was forged on the plains of Africa to help us hunt and gather, not to comprehend the nature of reality. These paradoxes teach us humility. They remind us that our perspective is limited and that the world is almost certainly grander and stranger than our minds can easily grasp. And finally, recognize our profound connection. Entanglement suggests that the idea of being a separate, isolated individual is a beautiful and persistent illusion. We are all, in a way that science is only just beginning to understand, part of a single indivisible whole. Perhaps this can inspire a deeper sense of empathy and responsibility for one another and for the world we share. The universe isn't broken. Our understanding is just incomplete. And the quest to resolve these paradoxes is the next great adventure in human history. I want to leave you with a couple of questions to ponder. Which of these paradoxes do you find the most unsettling, and why? And does learning about this strange quantum foundation change the way you look at your everyday world? Let me know your thoughts in the comments below. Thank you for joining me on this journey through the glitch in reality. Stay safe, stay curious, and take good care of yourselves and each other. And if this journey through the impossible has sparked your sense of wonder, please consider hitting that subscribe button and joining our community of explorers. There are many more mysteries to uncover together. Until next time.